first time I started carrying my own box of chalk. And I sleep well at night, so I don't have to be scrambling for chalk in the morning. Okay. Okay, let's transition now from talking about energy, joules, or work, and let's look at various kinds of forms of energy. And let's do a diagram up here. Okay, so energy can come in numerous forms, and these are pretty much all the major ones. You can sort of divide them down into other forms, but let's start with what we, kind of the examples I've been doing so far. Okay, what that would be called would be mechanical. Which is kind of a category of, it involves movement. Now that movement can either be, I'm going to artificially subdivide it into movement that we can see and movement that we can't see. Okay, so movement that we can see, we can call it mechanical, or we can call it kinetic. Okay, so kinetic is your car driving down the road, or a boulder rolling down a mountain. So since we can see it, you can think of as sort of macro kinetic. You can also have the movement of molecules. So that would be sort of micro kinetic. You can't see molecules moving, but when they do, and when they move faster and faster, we perceive that as heat. So you can also think of that as thermal energy. So that's actually over here. So you see mechanical and thermal energy are both involved with motion. It's just that when we're talking about thermal energy, we're talking about the movement of, so it's cool in this room, so the molecules in this room on average are moving slower than the molecules up in room 302 where they haven't fixed the air conditioner yet, right? And we feel that as heat. These two over here, nuclear energy and chemical energy, are all related to the forces that either hold an atom together or hold molecules together. So if we look at an atom, atoms are made up of essentially 3 types of subunits. The nucleus of an atom is made up, and for lack of a better symbol of drawing them, I'm just going to draw these little circles. So the nucleus of an atom is made up of protons, and neutrons. It's thought that the neutrons, since they don't have a charge, keep the nucleus together, because if you just put a whole bunch of protons together, protons have a positive charge, and positive things don't like to stay together because similarly charged particles repel. So the forces that hold the nucleus of an atom together are the forces that kind of keep this together. When you disrupt that and break it apart, that is called nuclear fission. And since it's a force that holds those particles together, when you disrupt that, it gives off a whole lot of energy in the process of splitting apart. So this is the basis of an atomic bomb, and this is also the basis of a nuclear reactor. Okay, so that is these forces here. Now, if you put particles together, that's what happens in the sun. That's called nuclear fusion. Okay, so that's in the sun, basically, we're taking hydrogen and turning it into helium. That's the major nuclear reaction that occurs in stars. Our sun is just a star. Okay, so those two are sort of opposite processes. Fission, you break atoms. Fusion, you put them together. Both are associated with an incredible amount of energy. We haven't figured out yet how to do fusion on Earth, but a lot of people are working on it. It happens naturally in the sun. There are also nuclear reactions occurring in the Earth, deep inside the Earth, and those are fission reactions, and a lot of the heat that comes from the planet, volcanism, plate tectonics, is a result of the energy that's given off by those fission reactions. The other atomic sort of level of energy are chemical energy, but those have to do with this these things that circle on the outside of a nucleus called electrons. I'm not going to get into a whole lot of detail, but two different atoms can combine in different ways, but those combinations are always involving the electrons. And you get the formation of bonds. So in water, for example, H2O, you have an oxygen atom, and it is sharing some of its electrons. This line here is a symbol for sharing the electrons with two atoms of hydrogen. Okay, so that's a chemical bond. It doesn't involve the nucleus directly. It only involves those electrons that exist on the outside of the atom. But when you break those bonds, so for example, if I have a long chain of carbons that are bonded to other things, and I start breaking those bonds, the breaking of those bonds also releases energy. So there's energy in this bond. And when I break the bond, I release energy. So common things like you sitting here breathing right now, you're breaking bonds just to live. Okay? Living, that aspect of living is a chemical process involving not nuclear reactions, but reactions that involve breaking bonds. So eating food, breathing, all those life processes are involved there. And also combustion, burning things, involves breaking bonds as well. So when you light a match, the heat that's given off is the energy of those bonds. So we've talked about the energy of motion, the energy of atoms over here, and then there's these two interrelated forms of energy. Here's electromagnetic energy. Okay, so electricity and magnetism are highly related forces. When you have a magnetic field, if you move a wire through it, you create an electric current. Or if you run an electric current, you automatically set up a magnetic field. So electricity and magnetism are sort of opposite sides of the same coin. All the electricity that we have in this building here running, giving us light, because in the United States you have places where there are gigantic rotating magnets. And those magnets are rotating, and there are big coils of wire associated with those rotating magnets. And because of that, that's how we generate electricity. We'll get into that in greater detail. What's wrong with this thing? So the energy that occurred, the fission that occurs in the sun, when that happens, it gives off electromagnetic radiation. So all the colors of the rainbow, that light, so light is in this category, but then things that we can't see. So I talked about the electromagnetic spectrum already. So gamma rays, X-rays, ultraviolet radiation, those are forms of the electromagnetic spectrum that we can't see. But again, that's just because of the limitation of our visual systems. And then there's just plain old electricity. So lightning, which comes from friction, and the electricity that we think of running through our electrical grid is all kind of related to that. So those are the major forms of energy. And again, for each one of those, there's an energy content. They are all capable of doing work. So as we start talking more and more about fossil fuels and, for example, burning coal, we'll be talking about how the energy in coal is transferred into the energy that runs through your wires that service your house. Okay? Any questions about these? Okay. Now I do want to turn it off. Let's see. It might be easier just to. Okay. So now we've got these various forms of energy. But we need some general principles to understand what happens with energy in the universe. So the first concept, and these are principles that were first discussed by Isaac Newton. And the first is called the first law . First law of thermodynamics. You know, we talked about hypotheses, talked about the scientific method. We didn't talk about laws. A law is really nothing more than a theory. So again, the pinnacle of scientific understanding. A hypothesis that hasn't been falsified. And the first law of thermodynamics basically says that essentially the amount of energy in the universe is constant. And if there's a constant amount of energy in the universe, that means we can't make new energy. Okay, so everything that's in you that keeps you operating is energy that you took from somewhere else. And it's thought that 15 billion years ago, all of the energy of the universe was focused in a single point, and that for some reason, no one knows why, that point for some reason just started to expand. Okay, that's called Big Bang. And that the amount of energy in the universe at that point hasn't changed. It's just that it was all highly organized and all put in one place. Of course, place doesn't really mean anything because there was nothing outside that point. You know, we can't, all space and time were condensed into that point. So there was really nothing outside of that. It's just that the universe was really, really tiny, like smaller than an atom. Everything that we know of now was condensed in that. I can't personally wrap my head around that. But that's what the math of the physics, of the astrophysics, seems to say. And ever since that point, the universe has just been continuing to expand and get larger and larger. And the amount of energy in that is constant. Now, what does happen, however, is as the history of that universe continues to unfold, certain forms of energy get transformed from one form to another. So we just had all those different forms up there. Even though energy is neither created nor destroyed, it can get transferred from one form to another. But that is now called the second law of thermodynamics. I'm not done writing, but let's just digest this for a second. So even though the total amount of energy in the universe is constant, what does happen is that one form of energy can get converted into another form of energy. That, by the way, is called energy transduction. Conversion of one form of energy to another is called energy transduction. And every time you take one form of energy and you convert it into another form of energy, a certain amount of that energy is lost. It's lost and turns into heat. Okay? And another way of saying that is that, let's say you start off with 1,000 joules of chemical energy, and you convert that chemical energy into kinetic energy. You're never going to get 1,000 joules of kinetic energy out. A certain amount is always going to be lost as thermal energy or heat. Okay? So what that tells you is that if the amount of energy in the universe is constant, and the only thing that can happen is one form of energy is transduced into another form of energy. And with every transformation, if we're always losing a little bit, it's like a tax that's paid on every conversion, then what's eventually going to happen to all of that energy in the universe? I've got, let's say this circle represents all the energy in the universe. And a little bit of that energy gets converted into another form, but this part of it goes to heat. So now we have this over here, which is that over there, and it gets converted as well, but that part goes to heat. Every conversion, I'm slicing off little chunks of heat. What's all of this energy eventually going to become? Heat. Or heat is just the kinetic movement of molecules. Okay? And this is called entropy. Okay? So the amount of disorder, another word we use for disorder is entropy. Entropy is a word for disorder. You can also think of that as just sort of general kinetic motion of molecules or heat. The amount of disorder in the universe is increasing. Which is another way of, yes?
Does heat, what's it called, transform into another type?
No. Generally, I mean, you can conserve it, but generally, and you can affect other energy transductions using heat, but generally, no. It doesn't convert back.
Technically, energy can be destroyed if one day it's all gone.
Well, it's not destroyed. It's just becoming extremely diffuse. Okay, because the universe is getting bigger and bigger, and all that energy that was in one spot is now spread out. And for a while, astrophysicists and astronomers were debating. You know, they all kind of admit that they know that the universe started with this big expansion, this big bang, but then they didn't know what was going to happen. Was it going to reach some state and start falling back in on itself? They call that the big crunch. So you have the big bang and the big crunch, and is the history of universes just this sort of oscillation between the universe compacting down or expanding? I'm not an astrophysicist, but apparently they've resolved that, and they think no, it's just going to keep getting more and more diffuse. Okay. I can't comment on that because it's not really my area of expertise. But you all are really kind of familiar with this. You might not know it. So do I have any homeowners here? Who's a homeowner? Any homeowners? Anybody own a house? You know people that do own houses. What happens if you stop cleaning out the gutters?
It's going to overflow.
Huh? It's going to overflow because what? What happens in the gutters?
Leaves pile up.
Leaves pile up. After the leaves pile up, what happens?
Starts decomposing.
Decomposing.
Stays there. Gets all clogged.
Seeds land in there.
Trees grow.
They start sprouting. Before you know it, your gutter is falling off. Okay? Then what happens to the water coming off your roof? Instead of going down through the gutter and being led away from your house. It goes right down the side and starts wearing into your foundation. Before you know it, you got water in the basement or you got foundational problems. That starts to crack. If you don't do anything to keep your house up, it's eventually going to fall into a pile of rubble. That's entropy. That's disorder. If you don't pick up your room, this is why your parents tell you, pick up your room, keep your stuff clean. If you don't pick up after yourself, you will eventually fall into disorder as well. Life, the process of being alive, is for a while we're cheating disorder. And if you think about it, your body is very organized. I have a digestive system, I have a circulatory system, I have an integumentary system, I've got skin. Okay? Those are separate compartments, and my body functions because those different compartments have different activities. When I get sick and when I die, you know, dust to death, you've heard dust to dust? Dust is disorder. You're alive for a while, but then you go back to being disorganized when you stop being alive. So ultimately, now if you can have kids sometime in the meantime before you die, then you pass on that order again to the next generation. But individuals eventually go the way of disorder. And according to the astrophysicists, the universe is going that way too. But we don't think that's going to be for billions of years. So we will never have to be around to experience everything becoming frozen and totally disorganized. Now, why is this important to the main topic of what we're talking about today, which we're getting ready to talk about fossil fuels? How is that related to? Yeah.
We're running out.
We're running out, and every time, everything that we do from our energy needs has to do with energy conversions. Okay, so we're getting ready to talk about petroleum. Petroleum gets refined into gasoline. Gasoline runs your car. Every time you run your engine, do you know what happens to the energy of most of that gasoline? It gets turned into heat. Actually, a high percentage of the running of your engine just basically heats up the engine. Some of it is converted into the motion of your wheels, and that pushes you down the road. But if we could get more and more efficient and capture some of that heat, or make engines more efficient, then we can decrease the amount of gasoline that we use so that we're using more of it to push your car forward and less of it to heat things up. All of the different fuel sources, all of the different forms of energy that we're going to be talking about, you can't get outside of these two. So far, nobody's been able to get outside these two laws. There was in the 1800s and the 1700s, when people were sort of looking at this, there was a challenge put out to people to come up with what was called a perpetual motion machine. Has anybody ever heard of that? Perpetual motion machine? Can somebody build something that will keep moving without putting any more energy into it? And nobody's been able to do it so far because of the second law of thermodynamics. Think about a pendulum. You've got a highly efficient pendulum here with some weight, and it's swinging back and forth. Well, eventually that pendulum is going to stop because wherever it connects here, and also as it's moving through the air, it's creating kinetic energy in the form of friction, friction with the air, friction with this point up here. And the reason the pendulum stops is because of the second law of thermodynamics. Because eventually all of the energy of the motion is slowly going to get converted into friction or heat and be lost as heat. And off into the universe it goes, not to be used again.
Is it possible to do that in a vacuum, since friction's a problem?
You can do it in a vacuum. That'll cut down on the friction with the air, but then you still have friction at the connection point. It theoretically should take longer to stop in a vacuum, but you still have where it's connecting up over there. So far, nobody's been able to do it because that's why it's called the second law of thermodynamics, because as far as we know, we can't think of conditions where the law doesn't apply. So when we're talking about burning coal to make electricity, when we're talking about an electric car that's pushing your, moving you from place to place, you always got to keep the second law of thermodynamics in the back of your mind. The best that you can do is cut down, bless you, is cut down the amount that goes to heat. And that's what's called efficiency. Okay, so if I start off with 100 joules and I do some energy transduction and I'm able to capture 50 joules and the other 50 goes to heat, okay, so that's a 50% return on my conversion. Well, if I, through engineering, can take that same 100 joules and turn it into 70 and only lose 30 joules, I've increased my efficiency. Okay, so that's, people are really interested in that because of, that could have to do with how you construct your house, for example, or the engineering of automobile engines. So, any questions about those?
I saw this one thing where they were using magnets for the perpetual motion thing, where they using a positive, negative part of the magnet to.
Mm-hmm.
Have you ever seen that?
Yeah. Well, maglev. Talking about like maglev trains.
I don't know. It was just this little wooden thing I saw. It was made out of metal with magnets hooked into it.
Well, magnets, like I said, magnetism and electricity are connected, and the way we generate electricity is using magnets. But like the energy that goes along our big power lines, as you increase the distance, transporting that electricity also, there's energy loss with that transfer as well. So you can't get away from energy loss. That's basically what the point is there. Let's go ahead and take a 5-minute break, or just a few minute break. You guys look like you need an energy boost. be back. Okay, let's get back to it. So we've talked about the first and second laws of thermodynamics. Now let's take a look at the places we go to essentially fuel all the things that we do in society. So this table is from your book, and it has a list of all of the energy sources here, and kind of describes them. You can read up on that in your book, and then essentially classifies them as to whether they are renewable or non-renewable. A renewable resource is a resource that regrows or reforms within So it's a resource that regrows or reforms, or is extremely large. And I'll kind of make a distinction there in a minute.
It's about trees and stuff.
Yeah. Within a reasonable time frame. And what we mean by a reasonable time frame is a time frame that's reasonable within the human time frame. So for example, you could plant a tree, and when you get older, you could harvest that wood and burn a fire with that. Okay, so that's a kind of a human time frame. So when we think about a reasonable time frame, we're thinking about a human time frame. So a non-renewable resource is any resource that doesn't do that. All right. So solar energy, for example. Now the sun, technically speaking, is non-renewable because the sun is burning through all of its hydrogen. And when it runs out of hydrogen, it's going to go nova and blow up, and the Earth will be no more. It's just that we think we've got a couple billion years of sun life left, so it's so huge we consider it to be renewable, because for any general human time frame, it's always going to be there, hopefully. Okay. Other examples, you plant a forest. Okay, so you plant trees for harvesting the timber. So within a reasonable time frame, those trees are going to grow and provide energy for you. Coal, on the other hand, the Earth isn't, as far as we know, the Earth isn't making any more coal. All right, so it's not regrowing or reforming. So coal is considered a non-renewable resource. So as you go through these, crude oil, natural gas, coal, and nuclear energy comes from uranium that we mine. Uranium isn't being reformed in any place that we can access it. So therefore, that's considered non-renewable. So whether a resource is renewable or non-renewable, that's a characteristic of the resource. Now, how we use that resource determines whether we're using it sustainably or unsustainably. So, sustainability is so unlike a renewability or non-renewability, sustainability is a characteristic of how we use something. So it's not a characteristic of the resource, it's what we do with the resource. So this is a characteristic So we can change the way we use something and shift from being unsustainable to being sustainable. So some resources, renewable resources, can either be used sustainably or unsustainably. So think about salmon. Anybody like sushi? I love sushi. Okay. Now if you go out and you use sophisticated trawling ships, you can basically harvest most of the salmon in the ocean. So much so that they don't really reproduce anymore. Okay? So salmon are a renewable resource. Given opportunities, they regrow. It's a nice characteristic about salmon. All right? But depending upon how we use them, we can either use them sustainably or unsustainably. You'll see, you'll be reading in your Aldo Leopold book, when he writes about pigeons, he's not talking about kind of the city pigeons we have today. He's writing about the passenger pigeon. There used to be billions and billions of passenger pigeons in the world. But we basically shot them out of the sky. They said their flocks were so big, it would take hours for a flock to pass overhead. It would be that big, and it would darken the sky. There were so many pigeons. But people like eating pigeons, so people would come out and just blast away at pigeons, and the last one died at the Cincinnati Zoo in the early 1900s. No more passenger pigeons. They won't regrow or come back anymore because we use them unsustainably. Okay? So renewable resources can be either used sustainably or unsustainably. How about non-renewable resource? Can you use a non-renewable resource sustainably? No, because it's not reforming. So you've got a finite amount of something, and if you use it, it's not regrowing. So there's no sustainable way to use a non-renewable resource.
So if you just cut down on it, I mean
you could cut down on it, but you're still using it. The only way to use a non-renewable resource sustainably is not to use it at all. You could leave it in the ground, and that way it'll be there. So do you see the distinction between these? A renewable resource is a characteristic of the resource. Sustainability is a characteristic of what we do with the resource. And we have no control over that. We can't turn the sun into a non-renewable resource. Okay? But we can control what we do with resources. So, out of our control, in our control. Now, I'd like to you know, rather than just have you learn all these, I kind of find that to be, these aren't, you know, they're sort of categorized with the non-renewable ones and then the renewable ones. But I find that drawing a picture, it's much easier to kind of learn these things. And it helps to start with the sun. We don't get all of our energy from the sun, but just about most of it. So let's think about, we're going to take these and kind of rearrange them into a picture so it'll help you to learn it. So solar energy, we said that's renewable, so we'll put a little R next to it. But when the sun shines on the earth and shines into the oceans or shines onto the land, it uses the energy to make biomass. That's over here. So biomass energy is directly related to the energy of the sun. What do we mean by biomass? All the plants, all the animals, everything that is a growing, living organism is biomass. We generally don't burn animals for energy, but we do burn plants. So prior to, say, in the 17 and 1800s and earlier, the majority of the energy we used in our homes was the energy of wood. People were burning wood. Coal sort of inched its way up, and then late in the 1800s, when petroleum was discovered in Pennsylvania, we started burning oil. But that's a fairly recent phenomenon. So for the majority of our time on Earth, we've burned wood. Okay, so biomass was really important. But the energy from that biomass came from the sun. And we'll talk about that in a minute. So because biomass grows back, we call it renewable. Now there's another form of biomass that occurred a long, long time ago and has sort of become compacted into the earth to form various geological formations. But nonetheless, it was biomass once. So I'll put a little dotted line here. So